This is a demo of my simulation on chaotic scattering. The line represents the trajectory of the particle, and the particle is this black dot. The contour lines represent height or depth in the scattering region. Here, these contour plots show a valley. Currently, the trajectory is plotted using Euler-Cromer integration technique. We can switch between the different techniques and we see that the path changes. And this depends on the accuracy of the technique itself. After running several experiments, we noted that Runge-Kutta 4 has a most accurate integration. Now, if we switch the contour plot from a valley system to a hill system, we see some changes. We see that instead of being attracted to the region, the particle seems to be deflected away. And this makes sense. It's harder for the particle to get across the contour region because now there are hills. And in fact, if we change the trajectory slightly, we see that it starts bouncing around in the middle of the hills. Now, when we look at the valley system, we see that if we change the trajectory slightly, the final output seems to be changing drastically as well. So right now, the scattering angle is about 22 degrees, but a small change later, the scattering angle is about negative 87 degrees. And this is where the chaotic nature of the system comes in. We see the same thing happening with the hill system, where small changes cause the output trajectory to be very different. So right now, it's going downwards, but a small change later, it seems to be going forwards. One more quick thing. Let's see what happens as we increase the initial velocity of the particle. So let's increase the x velocity. The particle seems to be able to jump across now, or it's initially going higher up the hill without any difficulty. It then turns around when the potential is too high. Let's see what happens with the valley system. A similar situation. We also see that sometimes the particle can get trapped inside a region. When it gets trapped, this is known as a periodic trajectory because it is trapped within a small region where it has periodic motion. Some of the patterns that are periodic are quite beautiful.